Today I'm going to be discussing U-substitution, otherwise known as the reverse chain rule. So let's say we had a function f of g of x. The derivative of this function would be f prime of g of x times g prime of x. Well, let's say you wanted to find the antiderivative or the integral of this function without knowing that, well, the answer to it because we started with it. Well, one way to do this is through a special technique called U-substitution, which I'm going to teach you guys about. So U-substitution is essentially setting a variable equal to u whose derivative is present. So we can make a substitution that will simplify the integral, making it easier to solve. So in this case, here we notice that the derivative of g of x is present. So we can make u equal to g of x, and the derivative of u with respect to x equal to g of x, or g prime of x. And what we can multiply is dx over, and we get that du is equal to g prime of x times dx. So now, after we make these notations, we know that we can make the following substitutions. This integral is equivalent to the integral of f prime of u times du. Well, excuse me, I forgot to write the dx at the end, but don't mind that, because this part is equal to, well, du. So now this integral seems a whole lot easier. In fact, it is easier. It's much easier to solve because now we know that the answer to this is simply f of u plus c. And after we make the substitution for u, we find that the antiderivative of this function right here is f of g of x plus c, which, if you recall, is precisely what we started with. So now I'm going to do several problems to show more examples of U-substitution, what can go wrong, and some more difficult scenarios. The first problem is as follows. Find the antiderivative of x squared plus 1 squared times 2x dx. So this was not that difficult. Almost immediately we noticed that the derivative of x squared plus 1 is 2x. So we can set our u to be x squared plus 1 and du to be 2x dx. So now we can say that this integral is equal to u squared times du. And now we can integrate this as if it was any other variable, and it will become 1/3 u cubed plus c. But we're not done. Remember, we have to substitute the u back in. So this will actually be equal to 1/3 x squared plus 1 to the third power plus c. And if you wanted to ensure that this was right, you could apply the derivative using the chain rule, and you could bring the 3 down. The 3 would cancel. It would become x squared plus 1 squared times the derivative of the inside being 2x. After applying the derivative, we see that we resulted with what we started with, and we know that we did this correctly. Let's do another one. This question, off the top of my head, or when we look at it, we notice that immediately there is no quick derivative where the derivative of 2x minus 1 is present, or the derivative of x, well, actually the derivative of x is present because it's just 1. But in this case, we're going to have to play around with the substitution a little bit more. So I'm going to set my u equal to 2x minus 1. So I'm going to do that on the side really quickly. U is equal to 2x minus 1. And du is going to be equal to 2 dx. So now we can make a substitution for the root of 2x minus 1, but we can't really get du because we still have the x left, which will make it much more difficult to integrate. So what you can actually do is we can manipulate this, and we can replace x. So if we move the 1 to the other side and divide by 2, we get that x is actually equal to this, which means that we can actually rewrite this integral as the root, or the antiderivative of u plus 1 over 2 times u, and I'm going to write it to the 1/2 power dx. And so now I'm going to multiply these together and take out the constant. So I can take out the 1/2, and I get that this is 1/2 times the integral of u to the 3 over 2 plus u to the 1/2 dx. And now I have to multiply by a 2 so I can get my du. So I'm going to multiply by a 2 on the inside, and I'm going to multiply or divide by a 2 on the outside. And this is going to become 1/4 times the antiderivative of u to the 3/2 power plus u to the 1/2 power du. Now we can integrate this as if it was any other equation, and it would become u to the 2/5 times u to the 5/2 power plus 2/3 u to the 3/2 power plus c, and of course we multiply all this by 1/4. And 1/4 times c is just another c, so we can just do this. And so yeah, this would be the antiderivative of this. However, as mentioned before, we are not done. We still have to make the substitutions back for our u. So we're going to go up here and we're going to make the substitution. So we actually have 1/4 times 2/5. Let's replace the u for 2x minus 1 to the 5/2 power plus 2/3 to the 2x minus 1, or times 2x minus 1 to the 3/2 power, and then we can close the parentheses and add the c. Wow, that was a mouthful. But this would be the antiderivative for that function using U-substitution. The third and final problem is relatively easy. So we have e to the x plus 1 times e to the x plus x. So immediately we realize that the derivative of this is present and it's right here. So we're going to make our u equal to e to the x plus x, and du is going to be equal to e to the x plus 1 dx. Oops, e to the x plus 1 dx. Okay, so immediately we notice, or not notice, we can rewrite this integral as the integral of u du. So now all we have to do is integrate this as if it were another variable, and we get that this is equal to 1/2 u to the second power plus c. And then all that is left to do is to replace what we substituted u for, and we have that this integral is equal to 1/2 e to the x plus x to the second power plus c. And that's it.